Welcome to a new era of navigation, where the AEON-CASIMIR craft redefines how vehicles move not by pushing against air or gravity, but by steering the very fabric of spacetime. In this chapter, we'll explore how classical concepts like thrust and inertia are replaced by geometric manipulation, allowing the craft to glide along custom-shaped geodesics. This isn't just a shift in technology, it's a paradigm leap in how we understand movement and control. Let's begin by setting the stage for this revolutionary approach to propulsion and navigation. Chapters 1 through 9 laid the groundwork covering propulsion, gravity, redistribution, and energy closure. Now, Chapter 10 focuses on how the AEON-CASIMIR vehicle is actually navigated and controlled when traditional forces no longer apply. The objective here is to explain the control laws and steering mechanisms that allow the craft to move seamlessly through space by altering spacetime itself, rather than relying on force vectors or classical acceleration. In classical flight, control is all about applying forces. F equals ma. But for AEON-CASIMIR, the rules are different. Instead of accelerating through space, the craft reshapes the local spacetime metric, guiding itself along a desired geodesic. This means the vehicle doesn't push against anything. It simply follows the path created by its own manipulation of spacetime curvature. The result is a fundamentally new way to move, one that's smooth, efficient, and almost entirely free of inertial stress. Metric steering is at the heart of AEON-CASIMIR's navigation. It's defined as the controlled, directional modification of the spacetime metric around the craft. When a steering input is given, it translates directly into a change in the local geometry, which in turn determines the craft's trajectory. The vehicle remains in a state of freefall, always following the path of least resistance through the spacetime it shapes. This approach eliminates the need for traditional thrust or lift. To maintain precise control, the AEON-CASIMIR system simultaneously tracks three coordinate frames: the internal coherent frame, locked to the craft's phase; the local external frame referenced to the planet or inertial space; and the global relativistic frame for astrophysical navigation. Transformations between these frames are continuous, ensuring that the craft's navigation remains smooth and accurate, regardless of its environment or mission profile. The AEON-CASIMIR's control system is built as a hierarchy. At the top is the intent vector, which includes direction, velocity, and temporal bias, essentially. Where, how fast, and when the craft should go. The next layer solves the Einstein-Casimir field equations to determine the required metric changes. Finally, the lowest layer actuates these changes using plasma rings, Casimir cavities, and electromagnetic boundaries. This layered approach ensures both flexibility and safety. At the core of navigation is the intent vector, which specifies the desired direction, velocity, and temporal bias. This vector can be set by a human pilot or by the onboard AI. It acts as the command input for the entire control system, guiding the subsequent metric solutions and field actuations. By abstracting navigation to this high level, the system allows for intuitive control, even in complex relativistic environments. Once the intent vector is set, the control system solves the constrained Einstein-Casimir field equations. This process determines how the local spacetime metric must be modified to achieve the desired trajectory. The solution takes into account both the pilot's intent and the vacuum coupling constant, ensuring that the resulting path is both feasible and stable. This mathematical layer is the bridge between high-level commands and physical reality. The final step in the control hierarchy is field actuation. Here, the solutions from the metric equations are physically implemented using advanced technologies like plasma rings, Casimir cavities, and electromagnetic boundaries. These components work together to reshape the local spacetime, enabling the craft to follow its intended path. The precision and responsiveness of this layer are crucial for safe and effective navigation. Directional movement is achieved by creating an asymmetric curvature in spacetime. The curvature is made deeper in the direction the craft wants to go and shallower behind it. This gradient in the effective potential causes the craft to move forward, not by pushing, but by following the path of least resistance in the reshaped spacetime. The result is apparent acceleration without any actual force being applied. Velocity is controlled by adjusting the magnitude of the curvature gradient. The greater the gradient, the faster the craft moves. Importantly, because the craft is always in free fall within its own metric, the occupants feel almost no acceleration, no inertial loads or stress. This makes even extreme velocities comfortable and safe for those inside. To turn, the AEON-CASIMIR doesn't rely on centripetal force. Instead, it rotates the curvature tensor, causing the craft to follow a new geodesics. This allows for right angle turns, instantaneous changes in direction, and complex maneuvers, all without imposing structural stress on the vehicle. The craft's path is dictated by the geometry it creates, not by forces acting upon it. Near planetary surfaces, the effective potential combines both planetary gravity and the vacuum metric. To land, the system gradually nulls the effective potential, increases decoherence, and allows Newtonian gravity to take over. This process is smooth and requires no hover thrust, making landings gentle and energy efficient. Time isn't just a background variable, it's a navigational axis. The system can bias the rate of internal time relative to external clocks, allowing for temporal buffering and synchronization. This feature protects occupants during extreme maneuvers and ensures that the craft remains in sync with mission requirements. However, backward time travel is not possible within this framework. Solving the complex field equations in real time is beyond human capability. That's why AEON-CASIMIR employs advanced AI systems to predict tensor solutions, enforce stability envelopes, and automatically gate decoherence. The AI ensures that only stable, safe metrics are implemented, acting as a safeguard against dangerous configurations. When operating near massive objects, the system dynamically overlays the external curvature of space with the craft's own metric modifications. This enables advanced maneuvers like orbit skimming, near-horizon traversal, and gravity well ascent or descent. The navigation system adapts in real time, ensuring safe passage through even the most challenging astrophysical environments. Safety is paramount. The AEON-CASIMIR system includes 3 hard safeties: metric relaxation, smoothly releasing curvature, coherence drop, restoring normal gravity, and Newtonian lock reverting to classical flight physics. All transitions are continuous, ensuring that the craft can always return to a safe operational state, no matter the circumstances. Externally, the AEON-CASIMIR craft is nearly invisible to conventional tracking methods. It emits no exhaust plume, produces minimal electromagnetic emissions, and follows non-ballistic trajectories. Radar tracking fails because there's no inertial acceleration signature, and its motion doesn't conform to classical kinematics. This stealthy profile is a direct result of its unique propulsion and navigation methods. Chapter 10 builds on the foundation set in earlier chapters: gravity sidebands, coherence enforcement, and energy closure. Without the navigation laws described here, the advanced propulsion methods would be uncontrollable. This integration ensures that every aspect of the AEON-CASIMIR's operation is harmonized, from energy management to safe, precise navigation. In summary, AEON-CASIMIR is not flown by pushing against air or gravity. Instead, it is steered by reshaping space-time itself. Navigation is geometric, not force-based, and the occupants remain in a state of freefall, even during extreme maneuvers. This approach makes high-speed, high-agility travel both possible and safe. The AI onboard AEON-CASIMIR is more than just an assistant, it's a critical component of safe navigation. By continuously solving complex field equations and monitoring system stability, the AI ensures that only safe, stable metrics are used. It acts as a guardian, preventing the craft from entering dangerous or unstable configurations and enabling human pilots to focus on mission objectives. Maintaining 3 coordinate frames simultaneously requires seamless transformations. The system ensures that the internal, local, and global frames are always in sync, allowing the craft to transition smoothly between different environments and reference points. This capability is essential for both planetary and interstellar navigation. Let's look at a practical example. A pilot sets a new course using the intent vector, specifying a change in direction and speed. Instantly, the system recalculates the required metric changes and actuates the necessary fields. The craft smoothly transitions to its new trajectory, with the occupants feeling no jolt or stress. This real-time responsiveness is a hallmark of the AEON-CASIMIR's advanced control architecture. The metric solution layer is where high-level commands are translated into mathematical instructions. By solving the Einstein-Casimir field equations, the system determines exactly how to reshape spacetime to achieve the desired motion. This layer is the mathematical engine that powers the craft's unique navigation abilities. Once the metric solution is determined, the field actuation layer takes over. This involves activating plasma rings, Casimir cavities, and electromagnetic boundaries to physically implement the required spacetime modifications. The precision of this process ensures that the craft's path matches the intended trajectory exactly, with no lag or overshoot. The key to directional movement is creating an asymmetric curvature in spacetime. By making the curvature deeper in the desired direction, the craft naturally moves forward, following the path of least resistance. This method eliminates the need for engines or thrusters, relying instead on pure geometry. Because the craft is always in freefall within its own metric, the occupants experience almost no felt acceleration. This means that even during rapid changes in velocity or direction, there are no inertial loads, making travel both comfortable and safe, regardless of the maneuver. To change direction, the system rotates the curvature tensor, effectively bending the geodesic path the craft follows. This allows for sharp, even right-angle turns, without any of the stresses associated with traditional flight. The craft's structure is never subjected to dangerous forces, no matter how extreme the maneuver. Landing is a controlled process where the effective potential is gradually reduced, decoherence is increased, and Newtonian gravity is allowed to take over. This ensures a smooth, gentle touchdown without the need for hover thrust or complex landing gear. The transition is seamless and safe for all occupants. Temporal buffering allows the craft to adjust its internal time rate relative to external clocks. This is especially useful during high-speed or high-gravity maneuvers, ensuring that the crew remains protected and synchronized with mission timelines. The system can also synchronize with external time sources as needed. While the system can bias the rate of time, it does not allow for backward time navigation. All temporal adjustments are forward-moving, ensuring causality and preventing paradoxes. This limitation is built into the control laws for both safety and consistency. The AI not only solves equations, but also enforces a stability envelope. It continuously monitors all system parameters, ensuring that the craft never enters an unstable or unsafe metric configuration. If instability is detected, the AI automatically gates decoherence or reverts to a safe mode. In environments with strong external curvature, such as near massive planets or stars, the navigation system overlays its own metric modifications on top of the existing space-time geometry. This allows for advanced maneuvers like orbit skimming and gravity well traversal, adapting in real time to changing conditions. If an emergency arises, the system can instantly engage one of 3 hard safeties. Metric relaxation gently releases space-time curvature, coherence drop restores normal gravity, and Newtonian lock reverts to classical flight physics. These modes ensure that the craft and its occupants are always protected, no matter the scenario. The AEON-CASIMIR's unique propulsion and navigation methods make it extremely difficult to detect. With no exhaust, minimal electromagnetic emissions, and non-classical trajectories, it evades radar and visual tracking. This stealth profile is a natural consequence of its advanced field architecture. Because the craft's motion is governed by space-time geometry rather than force-based acceleration, it does not obey classical kinematics. This means that traditional tracking and prediction methods fail, further enhancing the craft's stealth and unpredictability. The navigation laws described in this chapter depend on earlier developments: gravity sidebands, coherence enforcement, and energy closure. Each system is interlinked, ensuring that the craft operates as a unified whole. Without these foundational elements, advanced navigation would be impossible. Thanks to the geometric nature of navigation, even the most extreme maneuvers are survivable. Occupants remain in freefall, shielded from inertial forces, while the craft executes rapid turns or velocity changes. This capability opens up new possibilities for exploration and mission design. The AI's role extends beyond navigation. It acts as a safety net, constantly monitoring all systems and intervening when necessary, whether it's enforcing stability, gating decoherence, or reverting to safe modes. The AI ensures that the craft remains within safe operational limits at all times. Navigation is a continuous process, with real-time feedback between the pilot, AI, and field actuators. This closed-loop system ensures that the craft can adapt instantly to changing conditions, maintaining precise control and safety throughout every phase of flight. Unlike traditional craft, AEON-CASIMIR does not require hover thrust to remain stationary or land. By manipulating the effective potential and allowing gravity to reassert itself, the craft can land smoothly without expending additional energy. This efficiency is a direct result of its advanced field architecture. Temporal buffering and metric control work together to protect occupants during even the most extreme maneuvers. By adjusting the internal time rate and maintaining freefall conditions, the system ensures that the crew experiences no harmful effects, regardless of the craft's external motion. Because the craft's movement does not involve classical acceleration, there is no inertial acceleration signature for external sensors to detect. This makes the AEON-CASIMIR exceptionally stealthy and difficult to track, even with advanced radar or optical systems. To recap, AEON-CASIMIR's navigation is entirely geometric. The craft pilots space-time itself rather than flying through it. This approach enables unprecedented agility, safety, and stealth, setting a new standard for advanced vehicle control and propulsion. In conclusion, the AEON-CASIMIR craft does not simply fly through spacetime, it pilots spacetime itself. By leveraging advanced field architecture, AI-assisted control, and geometric navigation, it achieves a level of performance and safety unmatched by any conventional vehicle. This chapter marks a turning point in our understanding of movement, control, and the very nature of travel.